Look at the global energy landscape today, and you'll find an ocean of bioethanol. In 2021 alone, the world produced roughly 27 billion gallons, with the United States and Brazil churning out the vast majority. We celebrate this alcohol-based fuel as a triumph of sustainability. When blended with gasoline, it burns exceptionally clean, drastically reducing the particulate matter and toxic emissions floating in our atmosphere. However, our standard measurement for clean energy stops at the vehicle's tailpipe. This creates a massive data gap, ignoring the environmental ledger at the processing facility where the fuel actually originates. Growing, harvesting, and refining crops into fuel forces rural manufacturing communities to absorb heavy economic and ecological penalties. These costs stay invisible to the drivers filling up their tanks hundreds of miles away. To calculate the actual price of this renewable energy, we need to trace a single batch of ethanol through the industrial assembly line and measure exactly what gets left behind. Every drop of ethanol starts here, requiring a staggering volume of raw plant mass, usually sugarcane in Brazil, and massive fields of corn in the United States. This insatiable demand for biomass eats up millions of acres of farmland. It creates a system where fuel production directly competes against the local human food supply for soil, water, and space. But the deeper problem with crops like corn is the underlying math of their energy return. We have to look at how much energy goes into farming and processing the corn versus how much energy the final fuel actually holds. This chart compares the energy required to make corn-based ethanol against the energy it yields. As you can see, manufacturing a single gallon of this fuel requires 29% more energy to produce than it will eventually provide to an engine. That 29% deficit doesn't just vanish, it manifests as a massive, localized drain on the surrounding community's power grid, water resources, and heavy machinery fuel. Because this energy imbalance makes corn ethanol economically uncompetitive with gasoline, production relies on government subsidies. These subsidies are often recovered through heavy taxes on the public, which can trigger inflation across other sectors of the regional economy. Step 1 of the process proves that simply growing these crops systematically drains rural towns of both their land and their financial resources. Once harvested, the raw plant material leaves the fields and enters the biorefinery, a heavy industrial complex designed to break the crops down into their chemical components. To extract sugars from tougher, woody plant fibers, workers steep the shredded debris in vats of hot sulfuric acid. The acid violently dissolves the cellular walls to free the trapped carbohydrates inside. Other facilities use extreme heat to burn the plants into a synthetic gas. This thermochemical method quickly coats the inside of the machinery with problematic layers of tar and sulfur that have to be continuously scrubbed out. Even in standard fermentation, separating the alcohol from the remaining plant mush requires sending the mixture through massive distillation columns. This step relies on different boiling points to separate the liquids, which demands burning even more local energy just to maintain those extreme temperatures. And distillation can only concentrate the ethanol up to about 95% purity. The remaining water molecules hold on too tightly, requiring an intense final dehydration step to create fuel-grade alcohol. To strip out that last bit of water, refineries often inject harsh industrial solvents, like cyclohexane, into the mix. This chemical binds with the water and ethanol to lower the boiling point, forcing the final separation. This intermediate stage reveals exactly what it takes to produce bioethanol. It is manufactured in heavy industrial zones, completely reliant on toxic acids, severe heat, and dangerous chemical solvents. Once that pure ethanol is extracted and shipped off to gas stations around the world, we have to look at the massive volume of liquid sitting at the bottom of the distillation column. In sugarcane processing, this leftover sludge is called vinasse. It is a highly toxic, acidic liquid residue produced in staggering quantities. Vinasse holds absolutely zero energy value. It becomes an immediate logistical nightmare, requiring intensive, expensive chemical treatment protocols before it can be safely released or used as fertilizer. Refineries are also fighting a constant battle against bacterial contamination in their fermentation tanks. To keep the vats sterile, they pump in massive doses of antibiotics and harsh pH controls like ammonia, chemicals that ultimately cycle back into the local ecosystem. The end result of this assembly line is a stark geographic divide. The clean, polished fuel is exported to global markets, while the hazardous chemical waste is left sitting permanently in the local community's backyard. Looking at the full supply chain reveals the reality of ethanol. It is a resource-intensive industrial product with a significant manufacturing footprint. Commuters in distant cities might enjoy lower smog levels and cleaner air, but those benefits are subsidized by the local manufacturing zones. They are the ones paying the taxes, covering the energy deficits, and managing the acid treatments and endless pools of toxic vinasse. And this assembly line is only getting faster. Right now, major producing nations like Brazil are actively renovating existing plants, intending to ramp up synthesis to 2.5 billion liters of next-generation ethanol every single year. As global production scales to meet new aggressive renewable energy targets, the localized agricultural and industrial damage will compound right alongside it. Building a genuinely sustainable future requires evaluating the entire life cycle of our energy sources. Saving the planet cannot mean sacrificing the local communities tasked with powering it.